Welcome to This Explainer, where we're going to take those incredibly dense IEEE and IEC specifications for current and voltage transformers and, well, finally translate them into practical, everyday knowledge. We're breaking down the complexities today so you can approach your next electrical system design with total confidence. Let's get right into it.
Okay, let's dive right into this. What actually happens when you open circuit an energized current transformer? The short answer? A catastrophic failure. Seriously, we're talking dangerously high voltages, blown equipment, and a very real threat to life and safety. Getting these specs wrong has incredibly high-stakes consequences. But hey, don't worry. By the end of this explainer, we're going to completely demystify this alphabet soup of specs to keep your systems and yourself perfectly safe.
Let's start by visually grounding ourselves. Look at the diverse physical world of instrument transformers here, from those heavy-duty, molded cast designs all the way to the intricate relay setups. These are the actual, real-world physical devices we're dealing with today. We're building a solid foundation from the ground up, starting with how these units physically look and operate out there in the field.
Now, before we get into any complex math, we have to establish the absolute basic rules of the road when it comes to polarity. Think of it as a one-way street. If the primary current flows into the polarity mark, which you'll see designated as H1 in IEE standards or P1 in IEC standards, then the secondary current absolutely must flow out of the polarity mark, marked as X1 or S1. It's a simple, non-negotiable principle of directionality, and it really governs everything else we'll be discussing.
Building on that, let's look at the transformer ratio. Imagine you have a primary current of 100 amps and a secondary current of 5 amps. Your transformer ratio is 100 to 5. We just simplify that math by dividing both sides by 5, which gives us the 20-to-1 ratio you're seeing right here. It's that simple. It perfectly illustrates how that step-down proportion actually functions in the real world to scale down massive, dangerous currents into manageable, readable levels.
Moving on to Section 2, two distinct paths, metering accuracy versus relaying protection. We've officially reached a fork in the road here because current transformers really serve two totally different masters. On one hand, we need incredibly precise accuracy for revenue metering, right? Because that's literally how power gets billed and tracked. But on the other hand, we need rugged, unflinching durability for relay protection during massive, unpredictable electrical faults.
So let's explore that metering path first. Take a look at this standard IEEE burdens data. Now, the term burden might sound complex, but it's really just the load connected to the CT secondary expressed in ohms. All this data just represents standard ohm values from B0.1 all the way up to B1.8. Basically, it represents the total combined resistance of your devices and all your connecting lead wires.
Now, what's really interesting about this is how these out-of-class errors are visualized. This parallelogram maps out the IEEE CT metering accuracy limits. That inner box, that's your standard 0.3% class, and the outer one is the 0.6% class. If your calculated burden pushes you outside those lines, well, your metering is out of class and totally inaccurate. And more importantly, this proves that standard metering CTs have absolutely no accuracy guaranteed at current levels less than 10% of their rating. Simply put, low current completely ruins your accuracy.
So, if that's the somewhat fragile world of metering, let's pivot over to relaying accuracy. You'll often see protection specifications listed on a datasheet as something like C100 or T200. But what do these actually mean in the real world? Let's cut right through the confusion of these specific IEEE protection specs and just do the math. Okay, so that letter and number combination simply designates the minimum secondary terminal volts a CT can produce. Let's walk through the exact calculation. Step 1. Multiply your rated secondary current, which is usually 5 amps, by 20. That gives us 100 amps. Step 2. Multiply that by your total external burden. For this example, let's just say it's 1.0 ohm. Step 3, the result is 100 volts. And there you go, that is exactly what C100 means. This math just ensures your relay has enough voltage to push that massive current through the wire during a worst-case fault condition, all without exceeding a 10% ratio error.
To keep all this complex math practical, you really just need to memorize the three main enemies of CT accuracy. First up, low frequency. Second, a low current ratio. And third, high burden. If you ever mix high accuracy requirements with literally any of these three conditions, they're absolutely not going to be friends. You will lose your accuracy every single time.
And this brilliantly illustrates why we've been going through all this theory in the first place. When you look at a standard request for quote specification sheet,
Everything we just covered, the primary and secondary current ratios, the metering burdens like B.1 or B.5, the protection classes like C for IEEE, they directly map to the boxes you need to check off. Understanding the background theory directly helps you confidently fill out an RFQ spec sheet so you get exactly the right equipment for your system, no guessing required.
All right, Section 3, the take-home rules, crucial safety and installation guidelines. We are officially entering the climax of this explainer where all this theory becomes life-saving practice. You're going to want to pay very close attention to this part because getting these rules wrong can destroy your equipment or, honestly, much worse.
Before I drop these rapid-fire safety rules on you, just notice the stark visual contrast between these devices. We have a current transformer, which is a proportional current device, and a voltage transformer, which is a proportional voltage device. Now, they might look somewhat similar to the untrained eye, and sure, they sit in the same substations, but physically, they operate on fundamentally opposite electrical principles.
Which brings us right to rule number 1. Never open circuit a current transformer secondary while the primary is energized. Because CTs are proportional current devices, they desperately want to push current. It's what they do. If you break that secondary circuit, the voltage spikes instantly to try and bridge the gap. We're talking about dangerously high voltages that will cause severe equipment damage and put absolutely anyone nearby at a massive risk.
Now, contrast that immediately with rule number 2. Never short-circuit the secondary of an energized VT. Because voltage transformers are proportional voltage devices, shorting them out allows the current to flow completely unrestricted. Damaging, massive currents will surge through that secondary circuit, quickly melting wires and entirely destroying the transformer.
Okay, let's relieve some technical anxiety with Rule 3. Metering applications do not require a C-class CT. Remember our fork in the road earlier between metering and relaying? Well, those bulky, expensive C-class ratings are strictly for protection purposes, so they can handle fault currents. If you just need revenue metering, stick to metering class CTs. They're typically much smaller, significantly less expensive, and they're going to save you a ton of space.
So the crucial point here is Rule 4. CT secondary leads must be added to your CT burden calculation. Look, today's modern electronic relays themselves represent almost zero burden. In a lot of cases, the major resistance in the circuit actually comes from the long stretch of copper lead wire running all the way back to the control room. Forgetting to add the resistance of those lead wires is a super common, critical pitfall that will throw your whole accuracy completely out of class.
Rule 5 is simple, but it is absolute. Never use a 60 Hz rated VT on a 50 Hz system. It's a bad idea. A frequency mismatch leads to the internal core saturating much faster. This leads to severe overheating. And if you try to run a 60 Hz VT at 50 Hz, severe equipment failure isn't just possible, it's highly likely.
Finally, we have Rule 6. Exercise caution when connecting grounded VTs to ungrounded systems. If a fault condition occurs anywhere on an ungrounded system, the line-to-ground voltage on your VT can easily exceed its normal primary voltage rating. If that VT isn't specifically engineered and factory designed for that exact application, it's going to fail, and it's going to fail dramatically.
Let's wrap things up with a thought here at the end. If a single open circuit can destroy your equipment in the blink of an eye, are you absolutely certain your next spec sheet is perfectly balanced? Today we've covered the math, the accuracy classes, and those absolute non-negotiable safety rules that govern these devices. The stakes for getting these specifications right are incredibly high. Keep these principles close the next time you design a system. Thanks for joining me on this journey through the specs today.